Good day to everyone. We will be presenting our research entitled Development of AI-based Particulate Matter Monitoring Wearable Device for Welding Shops. A research by Reinhard Ashley Capistrano, Joel Salmo, Joel Lawrence Tinagu. Now, I'll introduce our research. Current stationary monitors cannot track the unpredictable fluctuations in welding fumes. This creates a blind spot for worker safety. Our research addresses this by developing an AI-based wearable. This system uses real-time data to transition from general room monitoring to personalized immediate hazard detection. For our general objective, we aim to develop a wearable AI-based system that monitors particulate matter in welding shops in real time. To achieve this, we have three specific objectives. First, to build the hardware prototype that detects PM1, 2.5, 10, as well as temperature and humidity. Second, to implement the multilinear regression algorithm which will predict PM concentration based on those environmental factors. And finally, to assess the device's performance by testing the accuracy and precision of its sensors. This study is significant as it addresses welding safety challenges using AI-based wearable, offering a data-driven solution to mitigate particulate matter exposures. For the welders, it's a personal alarm system for immediate risk. For management, it's a tool to keep an eye on their team's working condition. For the scope, our study focuses strictly on indoor welding environments. The device will monitor three specific particulate matter sizes, PM1, 2.5, and 10, along with temperature and humidity, utilizing a multilinear regression model. For the delimitation, we are limiting the AI aspect to the MLR algorithm based on our available dataset. Additionally, the system's accuracy depends on a single PM sensor and one temperature and humidity sensor. And the study does not account for uncontrolled environmental factors, such as changes in airflow or external weather conditions. For our research design, we have adopted the prototyping model. The process begins with gathering requirements and creating a quick design. From there, we build the initial prototype. The most critical part of this methodology is the iterative loop you can see here on the screen. We will evaluate the prototype's performance and based on the data, refine the device. We will repeat this cycle until accuracy is achieved, leading to the final implementation and maintenance phase.
Good day, my name is Jordan Sanago and I'll be presenting the system process flow. In welding environments, monitoring air quality is crucial because workers are exposed to heat, fumes, and airborne particles. Our system continuously tracks these conditions in real time. The BME280 sensor measures temperature, humidity, and pressure, while the PMS 5003 detects particulate matter levels such as PM1, PM2.5, and PM10. All data is sent to the SP30 microcontroller, where initial filtering and calibration ensures accurate readings. The ESP32 then uploads the process data to Firebase. A Python backend retrieves this information and performs linear regression to predict PM trends and identify potential air quality risks. This allows early detection of unsafe conditions, improving safety in welding operations. For the system architectures, the SP32 serves as the system's core, sending outputs to an OLED display, LED indicators, and a buzzer for warnings. The PMS 5003 and the BME280 provide the air quality measurements. 18650 lithium-ion batteries power the system through a TP4056 charging module and an LM2596 buck converter for stable voltage. All sensor data is transmitted via Wi-Fi to the database, where it can be viewed on a website for continuous monitoring and analysis.
Since our device measures PM concentrations, we have thresholds as seen in this slide to help determine air quality and guide when the alert should be triggered. We applied a regression-based approach that considers temperature and humidity to estimate particulate matter levels. This helps us understand how environmental factors influence PM behavior. All measurements are displayed in a web app that shows real-time readings and trends. This ensures that users can easily monitor air quality at any moment. Live readings from our device closely match those of commercial reference device, demonstrating strong real-time accuracy. Predictions from the regression model had low coefficient of determination values and higher errors due to limited training data, but they still captured general PM trends and the impact of environmental conditions. In conclusion, the device achieved strong real-time accuracy against commercial standards. Although the multilinear regression model showed weak performance for PM1 and PM2.5, and only moderate accuracy for PM10, the wearable device successfully captured breathing zone exposure that stationary monitors often miss. The prediction errors were largely due to limited sampling hours and environmental variability. Future work should focus on collecting larger and more diverse datasets to enhance AI prediction accuracy.